All right, so we're on the last chapter for this course. So this chapter 21 is called Paired Samples and Blocks. Although we're not going to be looking at the blocks portion. This really is the last section. We're going to we'll skip that part. So we're just mainly looking at the paired samples. Um, and so what we mean by paired samples is, and it kind of looks like we have two groups, but these groups can easily be paired. So if we look at this first example, recorded mileage for 1 year driven by 11 field workers on an ordinary 5-day work week, then recorded mileage for 1 year for the same 11 field workers on a 4-day work week. So as opposed to having two independent groups, we have two groups that are non-independent. And in fact, in this case, it's the same people doing the same, well, a similar thing 2 different times. And so we compare these mileages measured before and after the change. Expect drivers who drove more than others before the schedule change to drive more afterwards. And so we're not considering these independent groups. And so typically what we're going to do is we're going to look at how do these things change between the paired groups. So another example, only about 1% of people are truly ambidextrous. For the other 99%, how unbalanced is their dexterity? One common test measures the time it takes to place a series of cylinders into a set of holes. One experiment measured the time it took 93 children to complete the task using each hand. So again, we have two different samples, but they're not independent groups. They are the same group doing two different things. And so we can consider the pairwise differences. And so we have the times or the cylinders per second in this case, where each child did with the dominant hand, and then each child, same children, same group of children, did it with the non-dominant hand. And then we can subtract these two and see what the difference is. So you see most of these are going to be positive. We have a few that are negative. Now we can get the average of the differences. So we're not going to look at the average of the dominant hand and the average of the non-dominant hand and then subtract them. That's what we were doing with the groups, the comparing groups that we did in the last chapter. But here we are going to look at the difference for each individual person in the sample. And then we get the average of the differences. So we're really, as far as we're concerned, we're ignoring these first two columns and we're just going to look at the sample size for the number of pairs. So that's the main difference. So before we were looking at, we'd get the average of the first group, the average of the second group, and then compare those two averages. Here, we're going to get the difference for each set of data, each pair of data points, and then get the average of the differences. So it's a little bit different in that way. And they cannot be considered independent since it's the same child in this case doing each on the columns. So assumptions and conditions, data must be paired. There must be a natural matching. So obviously with the driving for the work week, we have the same driver driving one schedule and then the next schedule. With the kids, we have them doing one with each hand. For paired data, the groups are not independent, but we do need pairwise differences to be independent. So in other words, the differences, this is independent from that, is independent from that, and so on. So those do need to be independent, but this column is not independent of that column. So that's the difference from how we've been looking at these before. Assume population of differences follows a normal model. So this column, when we put it on a histogram, should be unimodal and symmetric. Even if maybe these, like if we put this column on a histogram, it may not be unimodal and symmetric. It could be skewed bimodal, etc. But the differences should be normal. So if we look at this example, so this is back to the driving example. Data are paired. Each value is mileage driven by the same person before and after the change. Behavior of any individual worker is independent of the others. And the differences are mutually independent. And then the histogram we can see is basically uniform or unimodal and symmetric. So we are good. We're good there. So we'll be doing t-test, and we'll be doing confidence intervals. And so I'll make sure to do examples of both. And so when the conditions are met, we can test whether the mean differences significantly differ from zero. So it's a little bit confusing with the wording there, but we're finding the differences for each of the paired data points. And we're going to see if the difference is greater than zero or less than zero, usually either way. So most of these will be two-test or two-sided test. So the null hypothesis is that mu equals whatever the difference is that we're looking at. Usually it's going to be zero. And then our test statistic, so d bar, that's the sample difference minus the population difference, which is usually zero, divided by standard error. Standard error is just the sample standard deviation of the differences over the square root of the sample size. So that's not that formula is really not any different than what we've seen before. It's just a little bit different notation because we're looking at differences, not just individual data points. So the D bar, like I said, in S subscript D, mean and standard deviation of the pairwise differences, and then N is the number of pairs. And then in this case, degrees of freedom, we go back to N minus one because we're really just looking at one set of data points. We're not looking at two sets of data points like in chapter 20. And then we can find the p-value. So let's do this. We're actually going to find a confidence interval. So let's find 95% confidence interval first, and then we will find the p-value. So we'll do both of these. So we have our summary statistics here. So on the calculator, we are going to go to stat test, and this is not anything new. We've done these before, and then we're going to go to t interval. And so on input, first line, we need to be on stats. And then our X bar will be the 0.499. Our SX is our SD in this case, 2.333. And N, of course, is 17. And then the C level is 95. And then we get negative 0.701 and 1.699 for our confidence interval. And so we can see that one of the things, and you may have seen this in the homework, we're testing to see, and we're going to test in the next part with hypothesis testing, if the mean difference is zero. And since the mean difference of zero would be right in, almost not quite in the middle, but fairly easily in the interval, we could probably say that the mean difference is not significantly different from zero, because it's zero is easily in that interval. If we were looking at the mean difference being -1, say -1 is not in the interval, and so we could probably easily say the mean difference is not going to be -1. But we can also test this with hypothesis testing. So our null hypothesis is going to be mu subscript D equals 0. We're going to assume that the difference is nothing. And then we're going to test to see if the difference is not 0. And so we can do a test statistic. And so using the formula up above, so the difference is 0.499. We're going to subtract 0, and we'll go ahead and do, you can do this part separately if you like, and then plug it in, but we'll just do it all at once. So that's our standard error, S over square root of N. And we put that in the calculator and we get 0.882. Now that is not a big t-score. So our p-value should be pretty high. So we can draw our curve if we like. 0 goes in the middle. We'll put our 0.882. This is a two-sided test, so we have negative 0.882 over here. And then our p-value, we're going to go to TCDF. We're going to multiply it by 2. And we have lower bound of 0.882, upper bound of 10 or 100 or 1,000, whatever you like. And then our degrees of freedom, again, is n minus 1, just like we were doing in previous chapters before chapter 20. And then we should get 0.391. So that's a very high p-value. So we would not reject the null hypothesis that the difference is 0. And so we'd say there is not evidence that the difference is 0 because the p-value is not small at all. So really, this is, as far as the calculations, this is not any different than what we were doing in chapter 18, I guess, or 17. These are just quantitative data, and we're just looking at the differences between two pairs of data sets. So nothing too complicated. Now we do see some examples in the homework and on the test review where we have a data set, and so we'll look at how to do these where we have a data set versus summary statistics. And so we'll find a 90% confidence interval and then do a hypothesis test for the mileage example. And so we have the data set here. We have the data set here. And so we're just taking that one minus that one, and we get the difference. So we're really only worried about this column here. So first, we need to input the data. And we did this back in chapter 2 or 3. So we're going to go to stat. We're going to go to edit, and we're going to put the data in L1. And we're going to put this data in. So just put that data in. If you need to clear the old data, move the cursor, highlight L1, hit clear, and then enter. And that will clear out the old data. You can type in this new data. Make sure you hit the negative button. Don't hit the minus button whenever you're putting in negative numbers. So always hit the negative that's under the 3. Don't hit the minus button that is next to the 6, or you'll get errors when you try to do anything. So once you get the data in, hit pause if you need to do that, and then put the data in. Once you get that in, we're going to go back to stat. We're going to go to test, and then we're going to go to t-interval. And now instead of stats, we need to select data. And then everything's pretty much done for us. You just need to make sure the C level is on 90%. And then hit calculate, and we will get 359.25 and 1604.7 for our confidence interval. So if we want to interpret that, we are 90% confident that the mean difference is between 359.25 and 1604.7. Then, now we can also do a what's called a t-test, which I guess we may have called it that before, but we've not used that on the calculator. So we can go again to stat edit or stat test with the data already in there. And now click on or select t-test. And again, we have input, and we can select data or stats. We're going to select data since we have our data put in. And our null hypothesis is 0. Our alternative, so I guess we don't really need this for the calculator, but so the null hypothesis is 0. The alternative hypothesis is not equal to 0. And so since it's not equal to 0, to get down to the mu, we're going to select not equal to mu 0. And then you can select calculator draw. Either one's fine. If you want to see the picture, you can draw it. If not, you can calculate. But then we see our t, our test statistic, is 2.858, and we see that our p-value is 0.017. So in this case, we would reject the null hypothesis. We would accept the alternative, and we could say that there is evidence that the difference is not zero. So, and you could do t-test for the one in the last example. You could try it out, and in that case, you would select stats and then put your summary statistics in there, and it would work. So that can be a shortcut for finding the test statistic and the p-value, either depending on if you have data or if you just have the summary statistics. So either way. Okay, so that's a fairly short chapter, not much in the homework and not much new in the calculations. But the main idea is that these two groups that we're looking at are not independent groups like they were in the last chapter, and we're really only concerned with the difference. So the difference, the pairwise differences, as it's called. So if you have any questions, let me know, and hopefully you've enjoyed this class. Hopefully you've learned something. But if you have any questions, feel free to email me, and I'll answer those.